All right, welcome to CECS 228. We're going to pick up on proofs part 4, which deals with recursion and the induction techniques that we've learned so far. So recursion deals with the process of defining an object or function in terms of itself. And to illustrate it, we have this example of a function called the is palindrome. Now, is palindrome is supposed to return whether or not a string contains a palindrome. And if you don't know what a palindrome is, that is simply a sentence or a word that is spelled the same way when you reverse the characters of the string as the original statement. So for instance, something very simple that is a palindrome would be mom, because if we reverse the spelling of it, we get the same word back. Another one would be like C's. This again, if you reverse the order or the characters in the string, you would get back the same string. And one that's a little bit longer is Madam, I'm Adam. Well, this one's a little bit harder to see because we have several characters, but if you take a look at the first and last character, they're the same, so that if we reverse it, this would be the first one, so at least we know that it would begin with an M. We can then take a look at the second character, which would get swapped with the second to last character, and that's also an A. We can check the third and check against the third to last, the fourth against the fourth to last, the fifth against the fifth to last, and finally this middle element is I, so when we reverse this, we'll get the same string back. And so this method is palindrome relies on that pattern in a palindrome text. So what it does is it looks at the first character and the last character, and if it's the same, if they're the same, then it can continue to break down, or it just takes the substring that omits the first and last characters to see if that substring is also a palindrome. So in this case, we would remove the two M's, we would leave the O, and then O is just one character, so we automatically return true at that point. Same as if we were to end up with an empty string. So like in this case, if I check the first and last characters, those are the same, then check the second. So we would, okay, so first and last characters are the same. That means we ignore them and just focus on the substring E and E. Take the first and the last character, compare against each other. They are the same, so we would ignore those. And at that point, we end up with a string that is empty. Okay, so if you end up with a string that contains one character or a string that is empty, then we know that for sure we have a palindrome. And so that is how this function works. It has a case for when the length is less than or equal to 1, meaning when it's 0 or 1, then we return true. Otherwise, what we do is we take the first and last characters, check if they're equal, and if they are, we call the same function is palindrome, but now on the substring that omits that first and last character. And so really it's this function call of is palindrome within the definition that makes it recursive, and that it's defined in terms of itself. So again, we're going to be looking at how mathematical induction allows us to prove that algorithms and functions such as these always return the correct answer. But in the meantime, in order to get to that point, let's go ahead and take a look at basic recursive functions. So a recursive function is defined using two steps. There is the basis step, which specifies the value function, the value of the function at 0, and I will add, it could also be at some other initial value. It's usually going to be the smallest element in the domain of the function. And then there's a recursive step, Well, we give a rule for finding the value of the function at integers that are greater than the initial value. Okay, so for instance, example 1 has this function f, which is defined recursively by f of 0 is 3, and f at n plus 1 is 2 times f of n plus 3. So this first part would be the basis step, and the second part would be the recursive step. Again, it's recursive because if you notice the current function value is based on previous function values or function values at other input. Okay. So using that definition, we're going to find f of 1, f of 2, f of 3, and f of 4. So let's start off with f of 1. Now, using strictly the definition here, if I want 1 to be n plus 1, that means that n would have to be 0. So f of 1 is 2 times f of 0 plus a 3. Now, f of 0, they tell us from the basis step that it's 3. So I'm just going to replace that in there. It's a 2 times 3 plus 3, which gives us a 6 plus a 3, and that is a 9. All right, now to find f of 2, again, 2 would lie, the way we would determine what it is by taking a look at the recursive step. So if n plus 1 is 2, that means that n has to be 1. So this is going to be equal to 2 times f of 1 plus 3, which is 2 times 9 plus 3, and that is going to give us a 21. F of 3 is going to be a 2 times f of 2, because really it's just whatever integer you evaluated in the step before that. So it's going to be f of 2 plus 3. That is a 2 times a 21 plus a 3. And so we get a 42 plus a 3, that's a 45. And last one, f of 4, 2 times f of 3 plus 3. That's a 2 times 45 plus 3. And that gives us a final answer of 93. Here's another example, example 2. Suppose that f is recursively defined by f of 0 is 1, f of 1 is 1, and f of n plus 1 equals f of n plus f of n minus 1. And then they're asking us to find f of 2, f of 3, f of 4, and f of 5. Let me just make a comment here. It wasn't explicitly stated, but this means that we are looking at n values that are greater than or equal to 2. And so we're going to include that. Same for example number 1. It wasn't clearly stated for the recursive step, but at the recursive step, this is defined for n being greater than or equal to 1. Just to know. Right, now what is f of 2? Well, if n plus 1 is f of 2, that means that n has to be 1 and n minus 1 has to be 0. So this is going to be f of 1 plus f of 0, which is going to give us a 1 plus 1, and that's a 2. Then f of 3, if n plus 1 is 3, then n has to be 2. So this would be f of 2 plus f of 1. F of 2 we just evaluated it's a 2, and f of 1 is given to us as a 1, so that's a 3. So if you notice, what we're doing is we're simply adding the previous two function values. To get f of 2, we add f of 0 plus f of 1, so 1 plus 1 is 2. Then we did 1 plus 2 is 3. Next, we're going to do a 2 plus 3 is 5. Just to stay consistent, let's write out the whole process. F of 4 is going to be f of 3 plus f of 2. F of 3 is 3. F of 2 is 2. So the answer is 5. And last one, f of 5, that will be given by f of 4 plus f of 3. and that would be a 5 plus a 3, which is an 8. Whenever we have recursive functions, we want to make sure that they are well defined. And so what does that mean? Well, a recursive function is well defined if for every positive integer, the value of the function is determined in an unambiguous way. And the value is the same regardless of how we apply any of the two parts of the definition. So for example 3, they're asking us to determine whether the proposed definition over the set of non-negative integers to the set of integers. And if it is well defined, we want to find a formula for f of n where n is a non-negative integer. We're also going to prove that the formula is valid. So let's take a look at part A. Part A has a basis step of f of 0 equals 0 and a recursive step of f of n equals 2 times f of n minus 2 for n being greater than or equal to 1. Well, the best way to, or initially what's the best way to check whether or not this is a well-defined function is to just plug in some values of n. And so I'll start with f of 1. If I want to find out f of 1, according to the recursive step, this is going to be equal to 2 times f of 1 minus 2, so f of negative 1. And, well, if I take a look at what's defined, I only have a definition for f of 0. I don't have a definition for what needs to happen when n is negative 1, right? The recursive step is defined for n being greater than or equal to 1, not for any negatives. So this is not well defined. And that's not well defined. Let's take a look at part B. And for B, we have f of 0 is 1, and then f of 1 is, if n is 1, then 1 minus 1 is 0, so we're going to have f of 0 minus a 1. If we want to find f of 2, that would be f of 1 minus 1. And actually, let me write out what the result would be. It would be 1 for f of 0, right, because f of 0 is 1, minus a 1, which is 0. And then f of 1, since it was 0, we're going to have a 0 minus a 1, which is negative 1 for f of 2. And just so that it's clear where these are coming from, I'm taking that result of 1 and plugging it into f of 0, or replacing f of 0 by that 1. Then the result of 0, or f of 1, I'm replacing it into this portion here. Let's go ahead and find f of 3. Well, f of 3 is simply going to be f of 2 minus 1, which is going to be a negative 1 minus a 1. And that'll give me a negative 2. And so I can start to see that, yeah, no matter what positive integer I try to find or try to evaluate the function for, I'm going to get an answer because this is well defined. It's well defined, meaning it's defined in an unambiguous way, and I'm getting results. Now the second part of the directions tell us that we need to find a formula for f of n that is explicit in n, meaning so that it is no longer recursive. It's no longer defined in terms of itself. And so what we need to do then is look at a pattern between the input values and the output values. And so this would be input, and this would be the output value. And, well, let's see, is there a pattern? When we input a 0, we get out a 1. When I input a 1, we get out a 0. Input a 2, we get out -1, input a 3, we get out -2. What it seems like to me, if we were to take a guess, it seems like the rule is that when you plug in n, you take 1 and you subtract away that n, right? Like if I plug in 0, 1 minus 0 is 1. If I plug in a 1, 1 minus 1 is 0. If I plug in a 2, 1 minus 2 is -1. So that's my guess initially. We still have to prove that it actually satisfies both parts of the recursive definition. So let's try to prove the correctness of this, and I'll just move this statement over. Okay, so to prove that the formula is valid, what we can do is first check that it satisfies the basis step. F of 0 is 1 minus 0, which is 1, so that checks out, right? F of 0 is 1. And then for the recursive step, I'm going to replace f of n with my guess. I have 1 minus n, and actually let me just rewrite the recursive step down here so that it's clear what we're doing here. I'm just replacing f of n with the definition. So I get 1 minus n. Is it true that that will be equal to f evaluated at n minus 1? So f evaluated at n minus 1 in my formula would mean that I would have a 1 minus n minus 1. So 1 minus n minus 1, and then I have to bring down this minus 1. So just so that it's clear, this is this. And the f of n minus 1 is this expression. Well, let's see. 1 minus n we can't simplify any further, so we want to check if it's equal to this right-hand side, and that we can simplify. If I distribute the negative, I'll have a 1 minus n plus 1 minus 1. Then the plus 1 minus 1 are going to cancel out, leaving us with a 1 minus n equals 1 minus n, which is a true statement. So because our formula satisfies both the basis step and the recursive step, that means that this is correct. All right, now we're going to move away from these simple sum and multiplication and look at exponents. They want us to give a recursive definition of a to the n, where a is a non-zero real number and n is a non-negative integer. And, well, let's see, remember in a recursive definition, we need a basis step. And the basis step defines what is the function value at the smallest possible element in the domain. Our domain is a non-negative integers, so the smallest non-negative number would be 0. Okay. So we need to define what happens at 0. At 0, if you have a to the 0, that is simply 1. Okay. And by the way, I'm treating f of n as a to the n. That's the function, but we're trying to come up with a recursive definition for it. Okay. What about the recursive step? Well, for the recursive step, notice that f of n, which again we said is a to the n, we can write this as an a times an a to the n minus 1, right? Because as long as you have the same base, you add the exponents. So if I add the 1 plus the n minus 1, I get n. Now, why are we writing it this way? Well, this a to the n minus 1 is f evaluated at n minus 1, right? This is equal to a times f evaluated at n minus 1. So we have found our recursive step then. In the recursive step, f of n is going to be defined as a times f evaluated at n minus 1, and this will be for n greater than or equal to 1. So altogether, our recursive definition will consist of f of 0 equals 1, and f of n equals a times f of n minus 1, for n being greater than or equal to 1. And that brings us to example number 5. Now, before we consider example number 5, let's just talk a little bit about what we saw in example number 2, which was the recursive function that was adding the previous two function values. And so this is what it looked like. Initially, we started with two given numbers, function values, 1 and 1. Then to get the next function value, f of 2, we add 1 and 1 to get 2, so that f of 2 is 2. Then to get 3, we added 1 and 2 to get 3. For f of 4, we added 2 and 3 to get 5, then added 3 and 5 to get 8. Now perhaps you recognize that because it's a very famous sequence. It's called the Fibonacci sequence. And often that gets represented using the notation f subscript n. So the nth Fibonacci number will be the n minus 1 Fibonacci number plus the n minus 2 Fibonacci number, for n being 2, 3, 4, and greater. And the initial conditions are that f0 is 1 and f1 is 1. And so we're just basically taking example 2 and rewriting the notation of the function so we have f sub n rather than f evaluated at n plus 1. Okay, so now with that being said, example number 5 is asking us to show that whenever n is greater than or equal to 3, f of n is going to be greater than alpha to the n, and this should say minus 2. It didn't quite print on my lecture notes, but hopefully you guys don't have that issue. Alpha to the n minus 2, where alpha is 1 plus the square root of 5 over 2, and f sub n is the nth Fibonacci number. Okay, so we are going to be using induction to help us prove this. I'm just going to start by writing the propositional function and its domain, and we'll look at the base case, and then from there we'll think about how to come up with the inductive step. And so first, we're going to let P of k be the statement that the kth Fibonacci number, fk, is greater than alpha to the k minus 2. And this is going to be evaluated at values k equal 3 or greater. Yes, because that's what they have for the statement, whenever n is greater than or equal to 3. Let's see if the base case is true. And actually, we might even need to prove more than one case. I've actually written this on a side work on a separate sheet just so that we wouldn't spend too much time. Oh, actually, I did it for, yeah, I did it for FP of 3. So. So using this defined function, here I used n instead of k, but it's essentially the same thing. P of 3 would be the statement that the third Fibonacci number, or Fibonacci 3, is greater than alpha. Now Fibonacci 3 is 3, so essentially what we're saying is that 3 is greater than the fraction 1 plus square root of 5 over 2. Yeah, so let's see if that is true. Now, alpha is this 1 plus square root of 5 over 2, which is definitely going to be less than 1 plus the square root of 9 over 2, because the numerator in this fraction is larger. And the square root of 9, we can simplify to a 3. So 1 plus 3 will give us a 4, and then 4 over 2 will give us a 2. Now that 2 is definitely smaller than 3. So that, and 3 is F3. So this shows that alpha is going to be less than 2, which is less than 3, and that is equal to F3. So the final conclusion is alpha is less than F3, so P of 3 is true. So, okay, that proves that P of 3 is true. Let's take a look if P of 4 needs to be part of the base cases. Now, before we do, I want you to notice something. Notice that if I take the square of alpha, that means that I'll have a 1 plus the square root of 5 over 2 squared. If I apply that square to both numerator and denominator, in the denominator I'll get a 2 squared, which is a 4. In the numerator, I'm going to have to distribute. So 1 times 1 gives me a 1. A 1 times the square root of 5 is square root of 5. A square root of 5 times 1 is square root of 5, so together it gives me 2 square root of 5. And then a square root of 5 times itself is just 5. So combining the like terms gives us a 6 plus square root of 2 over 5. 6 plus 2 square root of 5 over 4. And then we can separate the two terms so that it becomes 3 over 2 when we reduce the 6 over 4, and then plus 1/2 square root of 5 when we reduce the 2 over 4 here. Okay. Now, if we compare what we have for alpha squared versus alpha, this is just one more than alpha, right? Because alpha still has a square root of 5 over 2, and it has a 1/2 instead of a 3/2. So that's a difference of 1. That means that alpha squared is 1 plus alpha. Okay, so let's just keep that result in the back of our minds for now. It's going to come into play in what we're about to see for proving P of 4. Okay. So what is P of 4? P of 4 is a statement that F4 is greater than alpha squared. Reason being is that the function that we defined is that Fn is greater than alpha to the n minus 2. So if this is 4, this is a 4 minus 2, which gives us an alpha squared. Okay, so that's the statement that we're trying to prove is true. And what we're going to rely on here is the fact that F4 is a Fibonacci number, which means it's the sum of the previous two Fibonacci numbers, F3 and F2. And when we were taking a look at F3, or when we were looking at P of 3, we saw that F3 is actually larger than alpha. We proved that that is true. Okay, that was one of the things that we saw. So in this expression, F3 plus F2, that is going to be greater than alpha plus F2 because F3 is larger than alpha. And F2 is 2, so we get that F3 plus F2 is larger than alpha plus 2, and that in turn is larger than alpha plus 1. And that is equal to alpha squared by what we saw here in this work. So that boils down to F4 is larger than alpha squared, right? F4 is larger than alpha squared. So P of 4 is true. Okay, all right. Let's take a look at P of 5. Again, remember, what is the purpose in doing this? We are trying to see up to what case is part of the base case. Okay, and then what else just simply repeats, and whatever is repeating in the way that we prove is true, that we can make it form part of the inductive step. Okay. So for now, the way we proved P of 4 versus the way that we proved P of 3 is different. Okay? It's different not just because we decided to solve it differently, but because there was a different pattern to it. Okay? A P of 4 relied on the fact that alpha squared is 1 plus alpha. Okay. P of 5 would be the statement that F5 is greater than alpha cubed. Again, we're going to take the definition of the fifth of F5, which is a Fibonacci number. That's F4 plus F3. But F4 we proved is larger than alpha squared. So this sum is going to be larger than alpha squared plus F3. And F3, we said, was larger than alpha, right? F3 is larger than alpha. So we're now taking F3 is larger than alpha, or alpha to the 1. So together the sum, alpha squared plus F3, is going to be larger than alpha squared plus alpha to the 1. Now what can happen from here? I can pull out an alpha, and that's going to leave me an alpha plus 1. And alpha plus 1 is exactly alpha squared, so that gives us alpha to the 3rd. Okay, so that means that F5 has to be larger than alpha to the 3rd. Now if we do just one more so that we can check, because now it's starting to feel like a pattern, right? The way we proved that P of 5 was true looks very similar to how we proved that P of 4 was true. Let's see if the same can be said about P of 6. So P of 6 is the statement F6 is greater than alpha to the 4. If we split F6 into the sum F5 plus F4, that means that we're going to be using the result F5 is greater than alpha 3. So this sum, F5 plus F4, is going to be greater than alpha 3 plus F4. And then F4 in turn was larger than alpha squared. So we're going to have alpha cubed plus F4 is greater than alpha 3 plus alpha squared. And now we pull out an alpha squared, which is the largest power that they share in common, and we get an alpha plus 1 left over, which is exactly alpha squared, which is alpha to the 4th once you simplify. So F6 is indeed larger than alpha to the 4th. So, okay, so now for sure there is this pattern where we break down into the Fibonacci sum, and then we use the previous statements about what we have found is true. So like F3 is greater than alpha, or F4 is greater than alpha squared, in order to prove that the current Fibonacci number at n is greater than alpha to the n minus 2. And so where did we start seeing this pattern? We started seeing it here at 4, right, for f of 4. So the only one that's going to be part of our base case is proving P of 3. Well, let's do that. P of 3 is true because, well, alpha is equal to 1 plus the square root of 5 over 2 by definition, which is going to be less than 1 plus the square root of 9 over 2, because the numerator will be larger, which is equal to 1 plus 3 over 2, which is equal to 2, because this is a 4 over 2, and that is less than 3, and that's actually equal to F3. So that means that F3 is greater than alpha. Actually, just so that I make sure I don't run out of room, I'm going to rewrite it up here. Erase this portion. Okay, so that's the base case. Let's take a look at the inductive step. In the inductive step, we're going to assume that, well, we're going to assume that, let's see, that P of J is true. We can just say P of K. Let's see, I think we're going to have to assume more than just P of K, correct? Because we do have F of 3 and F of 2 and, well, okay. So actually, P of 4 was not proved like P of 5 because P of 4 used F of 2 being 2. It's not until P of 5 that we start seeing F of 4 is greater than alpha squared and F of 3 is greater than alpha by what we found in these two steps. And then for P of 6, we use that F of 5 is greater than alpha cubed and F of 4 is greater than alpha squared by what we found in the previous two steps. So P of 4 is actually going to have to be part of our base case. So P of 4 is true. Because alpha squared is equal to 1 plus alpha. Okay. So see side work. Hence, we obtain the following computation. F of 4 is F of 3 plus F of 2, which is going to be greater than alpha plus F of 2. This is by P of 3 being true. And that in turn is equal to alpha plus 2. And that is greater than alpha plus 1. And that is equal to alpha squared. What we get is that F4 is greater than alpha squared. Okay, now we can move on to the inductive step. The inductive step, we're going to start by assuming P of 3 and P of 4 and all the way down to some P of J is true for every J in the range of 3 to K, where K is some integer greater than or equal to 4. Now, what are we trying to prove? Well, we're trying to prove that P of K plus 1 is going to be true if this is true. And so let me just write that as our goal. The goal is to show that P of K plus 1 is true. So, i.e., that would be the statement that Fk plus 1 is going to be greater than alpha to the k plus 1 minus 2. Or in other words, that Fk plus 1 is going to be greater than alpha to the k minus 1. That's the goal. So let's work towards that goal now. Notice that since fk plus 1 is a Fibonacci number, then fk plus 1 will be fk plus fk minus 1. But since we've assumed that everything up to k is true, so p of k is true, that means that fk is going to be greater than alpha to the k minus 2 plus fk minus 1. And that in turn is going to be greater than alpha to the k minus 1 plus alpha to the k minus 1 minus 2, so minus 3. And this is since p of k minus 1 is also true. Then what can we do there? Well, then I can pull out the smallest of the two powers, which would be the k minus 3. And if I do that, I'll end up with alpha to the k minus 3 is alpha, it leaves me with 1 alpha plus 1. And then we know that alpha plus 1 is simply alpha squared, so this is an alpha to the k minus 3 times an alpha squared, which is going to be an alpha to the, well, k minus 3 and then plus 2 will give us k minus 1. So altogether what we've shown then is that fk plus 1 is going to be greater than alpha to the k minus 1 for some k. And this is going to conclude the inductive step. So now by strong mathematical induction, our statement p of k will be true for any integer greater than or equal to 3. Right, so the next topic is recursively defined algorithms. And basically what this means is it's just like a recursive function, except that this is, you can give it kind of like pseudocode that we write out in preparation for something that we want to code. So an algorithm is called recursive if it solves a problem by reducing it to an instance of the same problem with smaller input. Recursive algorithms consist of the following parts. So there's the base case in which we define how to solve the smallest possible case of the problem. And then there's a recursive case in which we reduce the size of the problem so that the result is still a problem of the same type. And then we apply the recursive algorithm to the smaller sized problem. And so to exemplify this process, we're going to look at example 6, which reads, give a recursive algorithm for computing a to the n, where a is non-zero and n is non-negative integer. So we've already come up with a recursive function, but not a recursive algorithm. So now think of it kind of like you're going to program this in Python, but you want to write out the steps first, that's precisely what we're going to do here. Okay, so first I'm going to start by defining a name for this function. Let's just call it power. And I'm not going to include the exact Python syntax. It's just think of it kind of like pseudocode. And power is going to take in two integers, the base a and the power n. Okay, so it's going to take a and n. Now we have to define what happens at the base case, at the smallest possible case of the problem. The smallest possible case of the problem would be when n is 0, right? That's the smallest non-negative integer. So we're going to say if n is equal to 0, then what we want to return is 1. So what we're doing here, I'll write it as a comment, is our base case. What happens if n is not equal to 0? Otherwise, if it's not equal to 0, if you recall the recursive function definition that we made, is we took a and multiplied it with f evaluated at n minus 1. So similarly here, what we're going to do is we're going to simply return, I guess I could write it on the same line, but I'll do it here. We can return a multiplied with the result of calling the function power with a, but now a smaller n, which is n minus 1. Okay, and so this would be now the recursive case. So here I'm just writing as a comment for ourselves. This is reducing the problem size, and the reason why is because we no longer have to calculate a to the n. We now have to calculate a to the n minus 1. And it's always a good idea to perform a trace through. So if we call, for instance, power with, let's say, 2 to the third, okay, what is that going to execute? Well, the first thing is it's going to check if n is 0, and well, it's not, it's 3. So we're going to go into this return, into this else return. So we're going to attempt to return a times the power of a with n minus 1. So it's actually going to go into another function call, right? Because it's going to return a times power 2 with 2. Okay, but power, this is not going to finish until power 2 with 2 returns something. So now we get into what does this do? Well, power 2 with 2 is going to again check if n is 0 and it's not. So we're going to go into this case where we try to return a times power 2 with 1. And we have a new function call. So now we have to take a look at what is power 2 with 1 going to do. Well, that is going to check if n is 0, it's not. So it's going to return a times power 2 with 0. And so we have one more function call. In this case, n is 0. So this is going to finally return 1. Okay, so this is going to return a times 1, which is simply a. Okay, so that a, I guess I'm going to rely on my highlighters now to kind of trace back, is the result of taking power 2 with 1. It returned A times 1, which is A. Okay, so this is going to return A times A. And that result was is going to be the return of power 2 with 2. So now this final one will be A times AL. And this whole time I've been keeping A, but it's really 2, right? Because our base is 2. So let me just change that to 2. So then this is going to return, and by the way, that's 4. So then this is going to return a 2 times a 4, which is an 8. Okay, so the final outcome of the return statement is this 8. Now we try power 2 with 0, that would just take one function call because we would go straight into this first block of returning 1. Where is the danger in using this algorithm the way it's written out? Can you guys detect any place where we might not ever return anything? Okay, well, if you said negative powers, you're absolutely right. If this is a negative 3, at the next step, or it's going to make a function call, return 2 times the times power of 2 with negative 4, right? Because we would be decrementing from negative 3. So we would do negative 3 minus 1 would give us negative 4. And then we would go to negative 5 and negative 6. It is never going to go into the case where n is 0, so it's never going to return this 1. It's never going to stop calling itself. And so that is a case of infinite recursion. It's an error that can happen when you're writing recursive algorithms. So sometimes to avoid that type of issue, we can say if n is less than or equal to 0, then you can return 1. But so I'm going to change this here to less than or equal to, just to avoid that problem. Okay, here is another example. Express the linear search algorithm as a recursive procedure. So linear search just simply means that you visit every element of an array or a list in order to find the desired element. So for instance, if we have a function called linear search, where I'm looking for the letter C in this list called alpha, what it would do is it would visit every single element in order until it either finds the element and it returns the index, or until it reaches the end of the list, in which case it tells you it's not found as part of it. Okay, so in this case, linear search would return a 2. In this case, it would return, sometimes it's written as -1 when it's not found. Or maybe just like a very negative number like -100 to signify we haven't found it. So how might we implement this recursively? Well, let's think about the operations that happen, right? Initially, I take the element C that I'm looking for and compare it against index at 0, against the first element of the list. And if it's not equal to that element, then I continue searching the rest of the list. Now the rest of the list, if we didn't have this element, if we just had B, C, D, E, F, that is the same procedure as what we did with the original list, which means we're going to compare against the first element B, and then if it's not that, we're going to continue looking at the rest of the list. So one way that we can implement it recursively is to compare against the first element, and if that is not it, we simply go ahead and break down the list into something smaller and call the function on the smaller list. Now, just to make it easier on ourselves, instead of actually returning the index, we're going to be returning true or false, and then we'll consider how to return the index in the coded homework. And so for now, this is going to return true or false when we apply linear search, look for some element, which I'll denote as ELE, short for element, and some given list, which we'll call array. Now, what would be the smallest instance of this problem? Well, the smallest instance would be if we have an empty array. If we have an empty array, then that means that it wasn't found. Okay? Or it means that we can't find the current element in the given array. So I'm going to say, I'm going to let n be the length of the array. And then we're going to say if n is equal to 0, then we're going to return false. Because you can't have an element in an empty array. Otherwise, we're going to check if the given element is the same as the first element of the array. Else, if the element is equal to the first element of the array, so array at 0, then we return true. We're going to reduce the size of the array to exclude that first element. So I'm going to create a smaller array, which is the result of taking an array and omitting the first element. So I'm going to sublist everything beginning at index 1 out into the end of the list. And in Python, the way we do that is with a colon and no stopping index, meaning continue. Then we return linear search the element, but now in the smaller array. So these go together and these go together. And that's our linear search. I encourage you to create a trace true. I won't do it just so that this video doesn't become incredibly long, but do try create a small array, maybe even like ABC, and check what happens when you try to look for A or when you try to look for Z, which would not be in the array. Okay, so we've come up with these recursive algorithms, but we haven't quite proved that they are correct. We've just made trace-throughs to kind of get a feel that they are working correctly. But just because we've tested it with 1 or 2 examples doesn't mean that they're going to be correct in every single instance. And that is why mathematical induction is so important to, in this case, computer science, because it allows us, or one of the many reasons is because it allows us to prove that a recursively defined algorithm is correct. So in example 9, they're asking us to prove that the recursive algorithm for computing a to the n from example 6 is correct. And from example 6, this is what we had. Power an is defined as If n is less than or equal to 0, return 1. Otherwise, return a times power, the same function, but now with a smaller n, with now being n minus 1. So let's give it a try. I'm going to let P of k be the statement. Power ak returns a to the k correctly. And this is going to be defined over a domain of k greater than or equal to 0. Now for the base case, we're going to prove that P of 0 is true. Okay. So P of 0 is true because, well, again, if you take a look at the algorithm, power A0 returns 1. And how do we know it returns 1? Because it goes into this first condition. So since n equals 0, and the if statement is executed. Now the inductive step. We're going to make the assumption that P of k is true for some non-negative integer k. Notice here we are using simply mathematical induction, not strong mathematical induction, because the truth of P power, or P of 1, is reliant only on the truth of P of 0, since power an is directly related to power at an minus 1, and not any other calls to power with smaller, like for instance, it doesn't depend on power a with n minus 2 or power with a with n minus 3. So because it's directly related to the number before it, to the power before it, then math induction by itself is enough. Okay, so now assume P of k is true for some integer k. So i.e. what that means is that power ak returns a to the k. Then what becomes our goal? Our goal is to try to show that P of k plus 1 is true, meaning power a to the a with k plus 1 will return a to the k plus 1. And so now we work towards that goal. Notice that power ak plus 1, and I forgot to mention this earlier, but this is true for some integer k greater than or equal to 0. So notice, since power ak, or power ak plus 1 returns power, or 8 times power ak, and that is because k is greater than or equal to 0, and hence k plus 1 is going to be greater than or equal to 1. Okay. So what that means is if k is at least 0, k plus 1 has to be at least 1. So we're not going to execute, or the if block is not going to execute. We're going to go directly into the else block. And so else, if this is k plus 1, we're going to return a times power a k minus 1. Excuse me, a k, not k minus 1, because this is k plus 1. All right. Now, by inductive hypothesis, power ak returns ak. So by inductive hypothesis, a times power ak must return a times a to the k, which is equal to a to the k plus 1. So that means that power a to the a, excuse me, that means that power ak plus 1 returns a to the k plus 1, and that is correct. This completes the inductive step. And hence, by mathematical induction, power an will return a to the n for any n greater than or equal to 0.